Alright, so we've seen single phase inverters, namely the half bridge and the full bridge inverters. We're going to look at in this video the three-phase version of the inverter. Well, a three-phase inverter. I mean, there are multiple different topologies, obviously, and when you get into applications that have to do with utility systems, there is an entire field of research dedicated to different topologies to achieve whatever functions you might want to achieve. And so we're going to look at the most common three-phase voltage source inverter. And so, I mean, we're motivated by the fact that certain applications, such as uninterruptible AC power supplies and AC motor drives, require three-phase inverters because they are connected to three-phase loads. We can either achieve this using single-phase inverters. We can use three single-phase inverters like the ones we've already studied. This may be favorable in certain cases, but usually, I mean, you end up needing a three-phase output transformer, or you need separate access to each of the three phases of the load, which is not generally available. And if you want a bipolar voltage, so if you want it to be positive and negative, then you'll end up needing 4 switches per phase. If you're using single-phase inverters, meaning if in a three-phase case, you'll have 12 switches. So what we're going to do is we're going to introduce the most common three-phase inverter. And the most common three-phase inverter is based on a sort of half-bridge structure. Although it's not a half-bridge inverter, it has 3 half-bridge legs, I guess, is what they usually call them in the theory. So you have one half-bridge leg like this, and then you'll have a second half-bridge leg like this, and then obviously a third one. So we have 3 phase legs, as they call them. And on the DC side, as we have had before, we'll have the DC link is split into 2 so that we can use one of these, well, I guess not one of these. This can be one of the references, right? Because here you have VDC over 2, and here you have VDC over 2. And there are multiple references that are usually used in this case. Sometimes it's also important to take the voltage here, or voltage with respect to this node here, and we'll call this node here 0 or O, however you want to call it, and this one will be N. And so essentially this is what the three-phase output of the inverter would look like. So depending on where you're taking the voltage with respect to, you might have VAO or VAN, let's say. But for now, I'm just going to call it VA, VB, and VC, and we'll assume that it's with respect to O, unless otherwise stated, right? So you might need to sometimes take it with respect to N. In other cases, you might define these terminal voltages in terms of the three-phase sort of neutral. So in some cases, you'll have a three-phase load, let's say, and this three-phase load, if it's connected in a Y configuration, might be connected in something like this. And then sometimes we call this N, and you can call this voltage VAN and VBN and VCN. But for most applications, you'll want to deal with your inverter side rather than defining things in terms of the neutral side, since you might not have access to that neutral side. But you do always have access to these line voltages. So another way to do it is the line-to-line voltages, right? So in this case, each of these voltages, VA, VB, and VC, are phase displaced by 120 degrees. Right, and you can have a positive or a negative sequence. We won't get into that. So positive and negative sequence just refers to whether it's A, B, C, or it's so it's A, C, B. So if you want to go this way, or if you want to go this way, it's whether it's called positive and negative sequence because the fact that the phase increases this way. And so in one case, you might have a positive sequence, which is this. So this is 120 degrees, whereas this one here is a minus 120 degrees. So that would be a negative sequence, right? Anyhow, those details are not so important for what we're dealing with here. Those have more to do with like the modulation and all that kind of stuff. But for what we're seeing here, we see that this is a three-phase inverter setup. So the output voltage of each leg, in this case, so VAB, VA, VB, and VC, is independent of the output load, since one of the 2 switches are always on. So we still have the same conditions, right? So if I call this, let's say, S1A, S1B, and then S1C, and S2A, S2B, and S2C, right? If S1A is on, then S2A has to be off. So we still have that condition that you can't short each phase. And so the switching is kind of left to the exact same situation as before, right? So you have complementary switching between these two, but as far as the rest of the phases are concerned, everything is 120 degrees phase displaced. So there is a sort of there are a number of ways to actually, I guess, memorize the way that these switching states, I guess, conduct. But one of the ones that I've found to be the most helpful, I guess, is from when I took a graduate course on this stuff. So the way that was taught there is that if we consider the switches, let's say A, B, and C. So this is for phase A, B, and C, okay? And I'm going to say P means positive, okay? So I'm only going to consider the top. So if P is positive, that means this switch is turned on, okay? So for instance, if I say O, 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 that means all of the top switches are off, okay? But if I say P, O, O, that means this one is turned on and these two are turned off. And obviously the complementary rule still applies. So what that means is if this one is turned on, if S1A is on and S1B and S1C are off, that means S2A has to be off and S2B and S2C have to be on, right? So you still have to have the complementary thing. And then you'll have P, P, O, and then you can have P, 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 right? So that's 4. And then you can have P, O, P, and then O, P, P. I believe there should be 7 in total. I think I'm missing one. O, O, P, I guess, right? O, O, P would be the other one. So you have these switching states. And so it can be any one of these combinations. And you can cycle through these either in a sort of natural way by just letting the PWM run the way it does, or you can have more elaborate ways of kind of, they call it space vector modulation, for instance, which we won't deal with at all here. But it's an advanced modulation technique where essentially you model the switching states as a rotating vector in space, and it allows you to sort of pre-program all of these states. But again, this is just to give you an idea of how the switching states can vary, and based on those different states, you'll have different voltages, of course, right? So for instance, if you have POO, what that means is this top voltage, that means VA would be, so that if this switch is closed, then VA would be connected to VDC over 2. So that would be a positive for this, and then you would have the phase B and C would both be negative, right? Because if it's POO, that means this is on, these two are off. If these two are off, so if S1B and S1C are off, that means S2B and S2C must be on, meaning voltages VB and VC must be negative, right? So you can work through each of the switching sort of conduction states based on this type of, I guess, analysis, if you will. And so, like I said, the output voltages are independent of the output loads and the load currents, because we're sort of forcing them based on these switching states. But if they operate based on PWM, and as we've seen in the past, PWM, and if you haven't already, I can link those videos in the description. But in PWM, you have basically the exact same thing as a single phase case, except instead of having a single modulating waveform, you'd have 3 modulating waveforms that are all 120 degrees phase displaced. So you would have 3 sine waves, you'd have 1 carrier. Each of these sine waves would be 120 degrees phase displaced. So this one might be 0 degrees, this one might be 120, this one would be 240. But they all compare with the exact same carrier, and they'll end up producing the required switching patterns. Still, we can look at, for instance, let's look at the line to neutral. So the line to neutral refers to this line, A, to, let's call it neutral, N. We're calling N our neutral point here, right? So in this case, VAN, let's say, and we'll say 1, so it's the fundamental, and this is the magnitude, so let's give it a hat so we can distinguish between the RMS if we want we want to consider RMS because we will after. So if this is the line to neutral, you have this, again, in the case of the half bridge, because this is essentially a half bridge, right? This is a half bridge, 2 switches, output is taken from the middle with respect to some point here. In this case, it's this point here. So VAN1 would equal K times VDC over 2, right? So that's the magnitude of VAN. Now, the same can be said for VB. However, VB itself, although the magnitude will be the same as VA, the phase will be shifted, right? So it'll be phase displaced relative to that by 120 degrees. Now you can also use this and you can find the line-to-line. We know that the line-to-line voltages from three-phase circuit theory, we know that line-to-line voltages are square root of 3 times larger than the line to neutral. So we can say that VLL1, let's say, and let's consider the magnitude first, the peak magnitude I should say. This will be root 3 VAN1, right? Peak. And so this would be root 3 times K times VDC over 2. Now if you want to find the RMS value, let's just leave that without a hat. That would basically be this thing divided by, so VLL1 peak over root 2, which would be root 3 over root 2 times K times VDC over 2. So that would be the magnitude of that line-to-line voltage. So you'd see it'd be larger, obviously, than the line to neutral. It would also be phase displaced by, with respect to the line to neutral by 30 degrees, right? So again, you can draw out the sort of three-phase phasor thing depending on the sequence that you have. You'll find that, I mean, if you have in this case A, B, C, and you want to find the line to neutral here, you would say A minus B. So you'd have A and then minus B would look like this. And then you can create your third vector. So that would be VAB. And this angle in here ends up being 30 degrees. And this magnitude ends up being root 3, right? So root 3 larger. So this type of stuff, we're not going to get into this type of analysis in these videos because it's assumed that you have this knowledge. And if you don't, you can always ask questions in the comments and we can deal with that stuff. So we also have a sort of generalized table because in the PWM, in the sinusoidal case that we saw for the full bridge inverter, we saw that there was a table of harmonics. Now we have the exact same type of thing for this, for the three-phase case, that is. And so here's the table of harmonics that we just saw, or that we were just discussing. And so the table of harmonics, I mean, again, it's the same, it's a similar one as the other one, but you'll notice you have a lot fewer harmonics, and this is because three-phase circuits, by virtue of the way that they are configured, eliminate a lot of the harmonics on their own inherently. So you have a lot fewer harmonics here, and you'll also notice that this is for a large and odd MF that is a multiple of 3. And so this table is taken from the textbook called Power Electronics, Converters, Applications, and Design by Ned Mohan. So I have to give credit where it's due, obviously. But this type of table can be found readily available, probably in any reference that you were to dig up on the internet. If not, you can probably generate one of these on your own. It might take some time to run through the simulations and do all this, but you can definitely run the Fourier analysis and develop a table like this on your own. And so the last thing that we would like to discuss here is perhaps let's take a look at how the waveforms look. So now this might appear complicated at first glance, but let's work through it step by step and see what we can do. Now we should also mention that some of these variables might be named a little differently, and I hope this is clear. But essentially this is saying VAR, VBR, and VCR. So this figure is considering R to be this reference. So maybe we can, for the purpose of this discussion here, let's just talk about this as R, okay? So VAR, VBR, and VCR. So it's this voltage with respect to this sort of reference. And maybe we can move this out of the way for now. I really wish we had more space, but this is a very big figure as it is. So maybe we just make it really large such that we can discuss it step by step and see what happens. Okay, so let's do it like this. So we see here, this is S1, this is defining the switching states. If you recall, I mean, I did it as POO and all this kind of stuff. So the way that this figure is doing it, it's calling the different switching states by different S indices, I guess. So S1 would be one of these, S2 would be, and we can probably look at what it is, right? So if this is POO, S1 is POO. And how do I know that? Because I said, remember, I said if this is P, the positive switch is on. OO in the top switch means that the bottom switches have to be on. And so what that means is in S1, the top switch is on, and then the bottom two switches are on for B and C. So this is POO. Maybe we write that in there. So this is P, this is OO, right? So the top switch is off, meaning the bottom switch is on, meaning the voltage is negative. And you can do all that here as well. So this would be PO, and then this would be OPO, and this is OPP, and so on. And you can continue. And since we're here, we might as well. So this is OOP, and then this one here, 6, is the same as this one. So this is POP. And since they're not considering the 0 state, they only end up with 6, right? I think we may have missed one then. So if OOO is gone and PPP is gone, so we only have 5. So which ones are we missing? OPO is missing. So we have an OPO. It's good that we pulled this waveform up. So we have an OPO, and we have a is that it? 6. Yeah, 6 waves. Never mind. We're okay. So yeah, those two I guess they didn't include because they are, I guess they call them redundant states, because one of them is 0 and one of them is just everything's inserted, so it's all positive. So you can use those in the space vector modulation, which is why I remember those from there, but I guess in the general case you can't really use them. Anyhow, you then have these AB, BC, and CA. So these are the line-to-line voltages, right? So if you have the output, if you have the outputs like this, taken from, and I won't draw the entire circuit, but if you have the outputs here, this is VA, and this is VB, and this is VC, let's say R, all with respect to R, then you'll have these voltages that exist between these lines, right? So this would be VAB, this would be VBC, and then you would have between here and here, you'd have VCA, right? And that's what these are. So you just take the difference of these, and you can analyze these waveforms directly in each state and find out that when you take the difference of these, you'll get these waveforms here. Now we won't do that obviously because that'll take quite some time, but that's what you end up getting. Now here you have VAN, VBN, and VCN. Now this waveform, the way this one is defining the N, so the neutral in this case is defined with respect to So the way that this one here is defining VAN, VBN, and VCN is this neutral is defined as the midpoint on the AC side. So you remember I mentioned that sometimes you have a 3-phase load, and the 3-phase load is connected something like this, and you want to find out what the voltage is with respect to this neutral, right? So that's what this VAN, VBN, and VCN is. So this would be VA. So I guess we can say this voltage here is VAN. This voltage here is VBN, and this one here is VCN, of course. And so, again, it's useful to have all these equations and all these waveforms and all these relationships to understand what's really going on. But you see that this is approaching somewhat of a sinusoidal behavior. So you want that, obviously. You want a 3-phase line to neutral, in this case, N being this neutral voltage that would be somewhat resembling a sinusoid, such that you can reduce the amount of harmonics. Now this one also takes the voltage N with respect to R. So this is sometimes depending on the system. So I mean, this is not always present because you don't always have a sort of, you might have an N connected directly to R, meaning this neutral on this side might be connected to this side here. So this is a sort of case-by-case thing. So let's ignore VNR for now because that's the neutral with respect to the reference node. So you would have voltages that look something like this. And if you were to sort of simulate this circuit in like Simulink or something like that, you would end up with waveforms that look something like this. So now the question, I guess, the last thing we can discuss is generating a PWM for something like this, right? So there are a couple of ways you can do it, but the best way to do it is probably to have a single carrier. So you'd have a single carrier. This is your carrier, and you would compare it. Let's say, well, let's give it a comparator. Let's just draw it as a block like this, so that we don't have to get into too many details. So that's your comparator block. And so what are you comparing? You're comparing basically 3 signals, right? So this would be, and these would be MA, or sorry, we'll call them K because that's what we did. KA, KB, and KC. And then your output would be essentially 3 switching pulses. In reality, you'd have 6, but because you have the complementary behavior, you would have, in this case, QA, QB, and QC, let's say. But these are your switching pulses, QA, QB, QC. And then these would go to your converter, right? So QA would go to, if we go look at this, QA, let's say here is applied. Let's apply QA here, and then we would apply the inverse of QA here. We'd have QB here, and we'd have the inverse of QB here, and we'd have QC here. Sorry, I wrote the inverse at the top too, didn't I? That's a mistake. And here we would have QC inverse. So the bottom would get the inverse, the top gets the actual pulse, for example. And these switching states would ensure that you would have no sort of cross-conduction sort of issues in terms of shorting things. You wouldn't have those issues anyways because of the way that the 3-phase ends up working out. So there was a lot that kind of happened here in a really short amount of time, it feels like. So this is the 3-phase inverter, the most common one. There are other ones, but essentially as long as you can achieve this functionality, you can produce 3-phase waveforms from a DC source. And so we looked at some switching states, we looked at what the fundamental magnitudes are, we looked at that there's also this table of sort of normalized harmonic components. We saw some waveforms and did some sort of further exploration of what's going on here. And then we saw this PWM technique. And so it's important to note here that Ka, Kb, and Kc would be sinusoidal. So that, well, assuming you want to produce sinusoidal waveforms, right? So these would be 120 degrees. So this one might be 0, this one might be 120, and this one might be 240, right? And so these are obviously degrees. Or if you want to produce square waves, these can be constants. And you can just compare with the carrier directly, and you can produce square waves in that way. So, but again, you might run into some issues because there might be cases where your square waves might overlap and cause some issues somewhere. In any case, this is as far as we're going to go here for as far as the theory is concerned for the 3-phase inverter. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.